small presentation of our novel optimal response strategy technique. Let's say we have a kind of gas supply network with loads and sources. Also, it may be equipped with the compressor plants, and in case we have a fault on the network, our goal is to create an optimal response strategy for this fault. What means optimal response strategy? We will need to do something. For example, introduce and activate additional supplies, or curtail, enforce a curtailment on some customers, or activate some compressors, so on. Let's first see our previous technique. So we have a time scale starting from T0, from the fault time, up to 3. It's up to moment when provisional repair work on the damage will be complete. It may be, let's say, 48, 96 hours. We have a time scale steps. In each time scale, different system states are possible. So I can mark with the point. Each point is a vector of state where. Each point is a vector of states where we have loads activated, deactivated, sources active and supplying, pipelines active, deactive, and so on. Each possible, we have possible version of state for each time period. In our previous version, each state was encoded as a genome, and using genetics algorithms here, let's say metaheteristic algorithms, most fit of them all was selected. What means most fit? This one when the minimal cost of state, what's the cost? Disconnected customers multiplied by social importance, or multiplied by factor. The factor in its nature, it's a social importance of the customer. So one of the possible states, with the minimum of social cost will consider the best one. Each state, when checked for fitness, metaheuristics always need us to establish a fitness function. They all are checked against feasibility criteria. So hydraulics calculus is performed, and pressure levels are checked, and flow speed in the pipelines is checked. So for each hour we will have the most fit one. Inertia was not considered, but what was made? We need to create a response trajectory. So, what behind the step? If we have a system states, each state includes, as I said previously, consumer states, supply volumes, and state of the pipelines, active links, active, activate, disactivate. Transfer from state to state, so if this is a state, we have an action. Action is a transfer between some of the actions will be a trajectory towards best solution. Without inertia, we can of course connect directly best or most fitting for each time interval. But such approach is dangerous because we can have something like this. For example, activate gas supply, but only for 1 hour. Sharp changes not needed. So it will be active. This source will be active in this state. One source will be active only for 1 time period. It's not a good idea. We can, let's say, introduce kind of safeguard against such situation, against such mistakes, by drawing a trajectory, desired trajectory, as a second degree, for example, polynomial or kind of approximation between most fitting points in each interval. Such flat solution gives us kind of estimation for the best trajectory and the best response strategy where the positive part. Such approach takes much less computing burden in comparison to full dynamic program when we need to consider all the spanning trees of possible solutions. For the quite large supply network, direct solution with dynamic programming, checking all the spanning tree of actions will be an unfeasible task. So such flat gives us not the most precise but acceptable solution. But it can be improved. Now, idea of improvement. We can still have a good performance and much better precision. So, what's the idea? Let's say we have time scale, same time intervals, and in each interval set of possible states. On the first stage, we perform genetics on the states, assuming that population for each, let's say, class, for each time interval, population consists of multiple states and our variables form a genome. So after first run, we will have a best fit, marked with red, these are best fit for each time interval. We can, of course, assume a set of action between intervals. Now, we can incorporate a second layer of optimization. First, we need to understand one moment. The space, functional space, where all this system, our gas supply system states are defined, has a matrix, because we perform a genetic algorithm on them. For each state represented as genome, genetic distance is valid and can be used. This means that this space is a matrix space. So we can set a distance between each particular element of possible states, let's say possible states community. So between each element of possible states community and the most fit, we have a genetic distance. This makes a sensible and reasonable idea of nearest, farthest. We can draw, let's say, something like this. Distance relative value of fitness function. Fitness. Relative value of fitness function as a function of genetic distance. So we will have if we set a margin line, for example at level 6, we will have a set of some limited it's a limited set of the states. We can drop not fit. Remaining set of the fitness gives us I will make them in green, selection of let's say best and its neighbors. Now, of course, we have a space of possible actions, meaning in general, meaning we have a set of possible trajectories. Now we can switch to the second layer. Second layer considers each trajectory as a population member. Points x for the first stage, x for the first time interval, x for the second, so third, and so on. These vectors of states are now elements of genome. Each population member has a genome of points. Should be noted, for each point we already know the fitness function, and each point already checked for feasibility. So for each point we know that this such a regime is plausible. It can exist physically. We have, let's say, red trajectory, blue trajectory, and so on. For I can draw also, for example, this will be green trajectory. For each we can perform a genetic optimization, the second layer of optimization. Now, trajectories being an object. We will have much less work comparing to classical dynamic programs because we already excluded all non-fit solutions. On the other hand, such approach, since we consider all the actions, is more precise, especially it's more precise on inertia. Here, actions are considered. So in short, we are building a set of trajectories based on the best fit from the first stage. And on the set of trajectories, during the mutation state, it's when we apply genetic, so in the heuristic, there will be a mutation and stage. Set of points is genome. It can be altered. So this second stage not operating with a fixed trajectory. No, they are flexible within preset distance, but the trajectories are flexible. So such approach much better reflects inertia. Two-stage genetic optimization much better reflects inertia, but it is known as to consider full decision spanning tree of decision as it would be for classical genetics. It takes more computing work, needs more computing labor comparing to flat solution only for each time interval, let's say at hope, but it's much less work than the classical, comparing to classical dynamic programming. And because of very fast convergence of genetic, it works in a it yields decision in reasonable time, and what's worse, it converges to global optimum. There is no problem with what could be with gradient techniques. No problem of binary values. With pipeline active, enabled, disabled is a binary value. There is no problem to incorporate a binary variables into genome. That's what good with this technique.